8.2a is looking at power functions and function operations. So we're still going to be using our radical rules and our exponent rules to simplify expressions, but we are also going to be talking about the domain. So remember that the domain is all possible input values, right? So anything we could plug in for x. So most of the time our domain is going to end up being x belongs to the real numbers, because it could be any real number, meaning it just couldn't be an imaginary number. However, we do have a couple of restrictions we have to watch out for. So restrictions that we'll see, for example, is that there's no negatives when your index is even. So say you had something like a fourth root, then x would be anything that's even, so anything greater than or equal to 0, because we can't take this even root of a negative number. So that would be undefined. We also can't have zeros in our denominator. So if we had something like 2 over x minus 5, well, if we set x minus 5 equal to 0 and we solve, we find that x cannot equal 5. So x could be any number in the real numbers except 5. So those are the type of restrictions we have to watch out for. So example 1, we just want to start off by simplifying a couple of these. So if we had 2x plus x plus 1, well, we're adding, so we don't need to distribute anything. So we just have 2x plus x, which is 3x plus 1. And there's our answer. There's no restrictions here, so our domain would just be the real numbers. Looking at this next one, 2x minus x plus 1. Well, when we have subtraction, you need to remember to distribute the negative. So 2x minus x minus 1. 2x minus x is x minus 1. There is our simplified answer. Again, there's no restrictions here, so our domain would still just be all the real numbers. The next one, we're multiplying 2x times x plus 1. So 2x times x is 2x squared. 2x times 1 is 2x. So 2x squared plus 2x. And again, there aren't any restrictions because we don't have any roots or any denominators to worry about. So x just belongs to the real numbers. Last but not least here, 2x divided by x plus 1. We can't actually simplify anything there, right? We've got 2 times x over the factor of x plus 1. There's nothing we can factor. We don't have any factors that can simplify out. So that's just our simplified answer. And then for our domain, well, x can belong to the real numbers, except we can't have our denominator be equal to 0. So if we solve, we see that x can't be negative 1. So x belongs to the real numbers, except it's not negative 1. But it could be any other real number. So let's go on and we'll solve a couple more. These next ones are using our function notation. F of x is 3 times x to the 1/3 power, and g of x is 2 times x to the 1/3 power. So now we have to think about our exponent rules. So if we want to find f of x plus g of x, well, I'm going to start by writing them down. F of x is 3 times x to the 1/3 plus g of x, which is 2 times x to the 1/3. So there are two steps here. Basically, we see if they have the same base, same exponent, same radical, and if they do, we can combine them. If we don't, we simplify and then try to combine them. So looking at these two terms, I see that for my variable, they both have x to the 1/3 power, which means they're like terms. So that means I have 3 of something plus 2 more of something, which gives me 5 of that thing. 5 times x to the 1/3. There's our answer. If you wanted to write it in radical notation, it would be 5 times the 3rd root of x. So then for our domain, well, it's an odd root, so we don't care about negative numbers. So x just belongs to the real numbers. Looking at f of x minus g of x, well, we have 3 times x to the 1/3 minus 2 times x to the 1/3. Well, again, they have the same term, right? X to the 1/3 power, same base, same exponent, so they're like terms, which means we're just taking 3 and subtracting 2, which leaves us with 1, x to the 1/3 power, or if you wanted it in your radical notation, that would be the 3rd root of x. And again, it's an odd root, so we don't care about negatives, which means our domain is just x belongs to the real numbers. So this is all we're doing. We're finding like terms, and if we have like terms, we can combine them. And in the next couple examples, we'll see a couple where we need to simplify before we combine them. Just as a side note here, if we had something like 3x to the 1/3 minus 2x to the 1/4, those have the same base, but they don't have the same exponent. So those are not like terms because they're not the same, right? You have to have the same base and same exponent before you can combine them. Moving on to example 3 here. Example 3, we've got 4 times x to the 1/3 is f of x, and g of x is x to the 1/2. So we need to keep in mind that our even roots means there are no negatives for our domain. So we want to start off by taking f of x times g of x. So f of x is 4x to the 1/3. G of x is x to the 1/2. Okay, well my coefficients are just 4 and 1, so 4 times 1 is 4. And then I want to take x to the 1/3 times x to the 1/2. So thinking about our exponent rules, our product rule tells us to add our exponents. So we want to take 1/3 plus 1/2. Well, hopefully you notice that 1/3 and 1/2 do not have a common denominator. So we need to make a common denominator. So 2 and 3 both go into 6. So I'm going to multiply by 2 and by 3, which gives me 2/6 plus 3/6, which is 5/6. So this simplifies to 4 times x to the 5/6. Or if you wanted to write it in that radical notation, right, our index is 6, so it would be 4 times the 6th root of x to the 5th. So this is our rational exponent notation. This is our radical notation. Well, now looking at it, we have an even root. So for our domain, we have a restriction here. We can't have any negative numbers. So our domain is where x is greater than or equal to 0. Because if it was, right, again, if we had a negative number, we can't take the square root of a negative, so that would be undefined here, which is why we have the restriction. Looking at the next example, f of x divided by g of x. Well, right, got to start by writing it out. F of x is 4 times x to the 1/3. And then g of x is x to the 1/2. So we're dividing, which means we're using our quotient rule. And our quotient rule says that when you're dividing two terms with the same base, you need to subtract your exponents. So we need to take 1/3 and subtract 1/2. Again, these aren't like terms, so we need to they don't have a common denominator, so we need to make a common denominator. So I'm going to multiply by 2, multiply by 3, which gives us 2/6 minus 3/6, which is negative 1/6. So now we have 4 times x to the negative 1/6. Well, we can't have any negative exponents. So thinking back, remember that if you have a negative exponent, you need to move it to the other half of your fraction. So this gives us 4 times x to the 1/6, which we could also write as 4 over the 6th root of x. Now, we also have to remember that we can't have any radicals in our denominator. So we have to take a second here and rationalize the denominator because we never want to have radicals in our denominator. So we need to think about what could we multiply in order to get the 6th root of x to simplify out. So we know we're going to have to multiply it by the 6th root of something, right? Because the only way you can multiply radicals together is if they're the same root. So if I have x to the 1st power, I would need 5 more x's in order for this to simplify. So I'm going to multiply by the 6th root of x to the 5th. Well, then my numerator is just 4 times the 6th root of x to the 5th. And my denominator, here's what happens. I'm going to draw it in a different color up here. We get the 6th root of x times x to the 5th, which is really the 6th root of x to the 6th, but the 6th root and the 6th power cancel each other out, so we're just left with x. So now we've got all even exponents and we don't have any radicals in our denominator. That's what we wanted. So this is our radical form. And if you wanted to write it in your rational exponent form, that would be 4 times x to the 5/6 over x. All right. And then last but not least, we need to do our domain. So looking at our domain, it looks like we still have that even root, so x can't be negative. And since we have x in our denominator, x also can't be 0. So x can be anything greater than 0. And again, that's because we have an even root with that 6. And since x is in our denominator, x can't equal 0. Let's do a couple more here. We want to take f of x times g of x. So we have x plus 4 times x minus 7. Well, this is just using our FOIL, right? X times x is x squared. And then we get minus 7x plus 4x minus 28, which leaves us with x squared minus 3x minus 28. And then looking at it, we don't have any radicals, we don't have any denominators, so there are no restrictions. X just belongs to the real numbers. Then we want to take f of x and divide by g of x. So that would give us x plus 4 divided by x minus 7. Well, looking at that, those are different factors, right? They're both completely simplified. So there's nothing we can do here. That's just our simplest form. And then for our domain, you're looking at our denominator. If x minus 7 equals 0, that tells us that x cannot equal 7. So x belongs to the real numbers, and x cannot equal 7. That's our domain. Last but not least, so these next ones have our exponents again. So we want to take f of x times g of x. So that's 5x to the 4/3 times x to the 1/3. Okay. Well, that would give us 5. And then remember, since we're multiplying, we're going to end up adding our exponents. So we have 4/3 plus 1/3. Okay, and again, we add our exponents because they have the same base. And so then our product rule tells us just to add. So 4/3 plus 1/3 is 5/3. All right. Well, that would be our rational exponent notation. And then if we wanted to write it in radical notation, we'd have 5 times the 3rd root of x to the 5th. But x to the 5th, we could actually simplify that. Okay, we'd have one group of 3 and then 2 left over. So this would be 5 times x to the 3rd root of x squared. That would be our radical notation. And then for our domain, well, we don't have a denominator. We have a root, but it's an odd root, so we don't care about that. X just belongs to the real numbers because there are no restrictions. So then last but not least, f of x divided by g of x. We have 5 times x to the 4/3 divided by x to the 1/3. Well, this is our quotient rule. So thinking back, our quotient rule tells us to subtract our exponents. Right? So again, these have the same base. That's why we can combine them. So our 5 stays the same, and then we're going to have x to the 4/3 minus 1/3. Well, 4/3 minus 1/3 is 3/3, and 3/3 is just 1. So 5x is our answer. And then for our domain, again, there's no roots, there's no denominator, so we don't have to worry about any restrictions, which means x just belongs to the real numbers. And that is it.